Okay, everyone. Now we're going to introduce the last part of the chapter 22. So today we're going to introduce an important concept, which is field. The field is widely used in many physics concepts, such as electrostatic field or electric field, or sometimes magnetic field. So let's introduce the concept from magnetic field, and we will talk about it mainly about electrostatic or electric field. So here, if we do an experiment like this, we put two magnets on the table, and then we put some iron filings, and we shake it, and then those iron filings will, let's say, iron filing sprinkles on the table. Then if you shake the table or your experimental device, like either a table or a container or something, then you will see those iron filing sprinkled surrounding the magnetics will be something like that. It's like particles connecting in lines, and those lines are the concept or the illustration of field, which is magnetic field. These patterns suggest that the space itself around the magnet is filled with magnetic influence. This is called magnetic field. The concept of such a field was first introduced by Michael Faraday. And then a field is a function that assigns a vector to every point in the space. And the alteration of the space around a mass is called gravitational field. So the gravitational field is everywhere surrounding the Earth. If you put something which has a mass surrounding the Earth, it will immediately have the force or gravitativity force between the Earth and the object. So that force is acted through a field, and we call this field gravitational field. Similarly, the space around a charge is altered to create electric field. So what does the electric field look like? Let's do another experiment. If we have a probe charge Q, which is shown here, and this probe charge Q experiences an electric force at a point in space, and then we say there is an electric field. And we use E with the arrow on the top, means it's a vector E at that point causing the force. So if we have a Q here and it has a force which is in this direction, then we will say at this point we have electric field which is E in this direction. And E could be calculated by F over Q. And E is a vector. F is also a vector, force is a vector, it has a direction. So E has the same direction with the force if your Q is a probe charge, means a positive charge. The unit of electric field are Newton per Coulomb. The magnitude E of the electric field is called electric field strength. If we put a positive charge here and we use a probe to measure the, let's say, the field or electric field surrounding this charge, you will see the directions and magnitude of those fields are shown here. So the electric field is created by a charge, and this charge is called source charge. So it has some features. Here shows 3 features. The electric force is a vector. Therefore, the electric field is also a vector. The field exists at all points in space. So here we take 1, 2, 3, 4, 5, 6, 7, 8, 8 points as our probe points to collect the direction and magnitude of the field. Actually, the field is everywhere. If you put your probe at any place, you can measure the field at that place. A charge does not feel its own field. Let's say this positive charge, it doesn't feel its own, it doesn't feel the electric field created by its own. That's electric field. If the electric field at point in space is E, then a particle with charge Q will have a force at that point, which is the force equals Q times E. If the charge is positive, then the force is in the same direction as the field. In the opposite way, if the Q or the charge is negative, then the direction of the force is opposite to the field. Now let's see one example about electric force or electric field. So every cell in your body is electrically active in various ways. For example, nerve propagation occurs when large electric field in the cell membrane of neurons cause ions to move through the cell walls. The field strength in the typical cell membrane is 1 times 10 to, it should be negative 7 Newton per Coulomb. What's the magnitude of the force on such at such a field on the calcium ion? So that's easy. We know the field, we want to calculate the force, and we need to know the charge because force equals the charge times field. So the ion is a point charge in an electric field. A singular charge ion is missing 1 electron, has net charge of Q equals to E. Then we know Q times field equals to force. So that's easy. F equals to charge times field. You just take all the numbers and you get the forces. So the force is this number. Okay, now the electric field of point charge. If we have, let's say, a probe charge, which is Q prime, here, we want to calculate the field at this point, which is generated by Q. So what we can do is we first calculate the force using Coulomb's law, and then we use the force over Q prime. It will be the E. Then let's do it. First, E equals the force over Q, and the force is Coulomb's law. It's a 1 over 4 pi epsilon 0 Q over R. Actually, it should be Q times Q prime. And then here you have a Q prime. Then the Q prime cancels the Q prime. Then the field equals to 1 over 4 pi epsilon times Q over R squared. It's a very similar to Coulomb's law to calculate the force. The only difference is the other Q prime is canceled out. If we calculate the field at sufficient number of points, let's say you take a lot of numbers surrounding the point charge, then we can draw a field diagram. So here shows the field diagram. The arrows show the magnitude and direction of the field. Notice that the field vectors all point straight away from the charge Q. And also notice how quickly the arrow decreases. Why it decreases when it's getting further away from the Q? Because the E can be calculated by using this equation. So it's something over R squared. So when R is doubled, then the electric is becomes 1/4 because it's 1/r². So it's the electric field decreases quickly by the inverse r². Now, another concept, which is unit vector notation. So for example, if we have a positive charge here, and then we have some probes like position 1, 2, 3, and then we know the magnitude and directions of the electric field could be denoted by 3 arrows. The arrows are bigger when the electric field is stronger. So here we can also define the direction of vector simply by using r hat. This is called unit vector. The unit vector r hat specifies a direction of a vector. Let's say here we want to use a vector or unit vector to indicate the direction of the electric field at some positions. Then we can use r hat. That's what we need to describe the electric field vector at points 1, 2, 3 due to a positive charge at the origin. The electric field E points in the direction of unit vector R. So once we learned the unit vector R, we can denote the electric field by magnitude times the unit vector R. And here, one thing we need to be careful is that unit vector, it doesn't have any unit. It's not in 1 meter or 1 centimeter. It doesn't have a unit. It only has the direction. So no unit is assigned to a unit vector. So the electric field of a point charge, using unit vector notation, the electric field at the distance r from point charge is E equals to 1/4 pi epsilon times Q over r². And then if you want to calculate the vector E, see this is arrow above E means the vector E, then it equals the magnitude times a direction, which is the unit vector r hat. So that's a unit, that's a vector format of electric field calculation equation. A negative sign in front of vector simply reverses its direction. This figure shows the electric field of negative point charges. Okay, one more example. The electron in a hydrogen atom orbits the proton at a radius of 0.053 nanometer. What's the proton's electric field strength at the position? And what's the magnitude of the electrostatic force on the electron? So that's an easy question. We can directly use the Coulomb's law to solve those questions. So we know the distance, and then we need to know the charges to calculate the force. Let's see. First, let's calculate the field. The electric field equals to E equals to 1/4 pi epsilon charge over a distance. The charge is E, it's a unit charge, which is 1.6 times 10 to -19. And then R is a distance. It's given in the problem. Take all the numbers into the equation, you can calculate the result. This is the E. Now let's calculate the force. Force equals to field times charge, and then take the numbers, you get the answer. That's pretty straightforward problems. So that's all for the entire chapter. So in this chapter, we have learned many concepts about charges and then conductors, insulators, and then Coulomb's law, and then we introduce the electric field. So the calculation in this chapter is not much. You mainly need to remember Coulomb's law. And then what you need to do for calculations in this chapter is just plugging in all the numbers, and then you will get the answers. So for chapter 1, it's not difficult, but please learn it and read the textbook carefully and do your homework on time. Thank you. I'll see you next time.